So the last part is the fast part. Characterization of systems. So we're going to talk about a couple. We're going to talk about linear systems. All the systems we study at an undergraduate course are always going to be linear systems. And that means two things. That means first, scaling. In other words, if we know that x of n goes into a system and causes a particular output, the scaling property means if we multiply it by a constant a, then we can multiply the output by a. In real-world systems, that's not strictly true. At some point, if you put in a large enough input, if you put in 10 billion trillion, at some point the system's going to break. But for small changes in inputs, that's a very effective approximation that your system is linear. And the other is the superposition principle, which says that if x1 through our system causes y1, and if x2 causes y2, then if we add these two guys, add the two inputs, we can add the two outputs, and that will be valid. So if this, then this. All the systems we do so far will be linear. I'm going to let you look in your text for more detailed examples about what that means. It would take up probably an hour to go through all the different possibilities of what that means. But the text does go through some good examples. And this shows the intuition you need to understand what linear is. The next is time invariant. All undergraduate systems will always be linear and also time invariant. And I think the easiest thing to understand, the easiest way to understand what time invariant systems are is intuitively that if your system is as an example, a high pass filter today, it will be a high pass filter tomorrow. This is how I would think of what time invariance actually means. You know, another example is that h of n, this is a little bit more rigorous, does not change. Holy cow, what would it mean if it did change? If it did change, it would mean that h of n is not only a function of h of n, but also a function where n is your independent variable, but also a function of n1, the particular time that you are using it. Now again, systems, giving a more global perspective here, systems in general don't always stay the exact same through any period of time. If you take a look at the relationship between temperature on the Earth as a function of season as during the year, you can be pretty sure that our average temperature on the Earth versus day in say in Virginia for January through January this year is going to be similar to January through January of last year, but 100 million years ago it was noticeably warmer. So it's not strictly time invariant taken in extreme, but it's a really good approximation for what we would typically consider systems. So a system, if you're looking at how a missile again launched, that missile might behave. Well, a missile is a single launch device, but if you looked at how at the dynamics of how a gun, a 2.7, if you looked at the dynamics of how a machine gun fired, it would probably be slightly different after it's fired 10,000 rounds than on day one. So that's an example of a non-time variant system. But for the systems that we study as an undergraduate, they are all linear and time invariant. And that is so common that we're just going to call them LTI systems. Some other characterizations of systems has to do with causality. So a system is causal if y of n only depends on current or past inputs. If your system, if your response to me pushing you is the system, if I push you, you're going to move. You're only going to move after I push you. You're not going to move suddenly a second before I go up and push you. So that's an example of a causal system. An equivalent way of saying that is h of n is 0 for n less than 0. If you give it an impulse response, its response only changes after you've hit it with the impulse. That seems like a no-brainer, right, for a system in the time domain. But remember, in a discrete time, n doesn't have to necessarily refer to time. It could refer to location, position, in which case you could have a non-causal system. When you throw a pebble at a pond, it moves ripples in both the right and the left direction. We have bibostability. We talked a little bit about that before. Bibostability means bounded input. If your inputs are bounded, then your outputs will be bounded. So as an example, one way to test for that is that your sum of your impulse response is strictly less than infinity. And if that's true, then your system is bibostable. A simple example of one that's not bibostable is the accumulator we just studied. Your output is equal to your input plus your previous output. Because if your input is a step, then you can see your output grows. The last thing we want to cover is lossless and its related concept of is it passive. And lossless is if the output energy is equal to the input energy, then it's lossless. So how do we define energy? The energy of a signal is equal to the sum over all space of the square of your signal. Absolute value of the square of your signal. And then passive is the exact same thing. It's just if your output energy is less than or equal to your input energy, then it's passive. And that's it.